Today, we're going to work on paradigm shifting. How do we work on the structures that have informed how we do what we do? For many of these structures, we need to disassemble them and rebuild them to match the realities as they are, not as how we've been taught to perceive them. One of the most important such shifts I have made was occasioned by Buckminster Fuller teaching us to think about the Earth as our spaceship, as it really is, in all of its natural glory. We're not adversaries. None of us are. We're all crew members. What do crew members do? They work together for the benefit and the survival of the whole ship. That's what we must do now across the globe. All right, what's our problem? The emissions from burning carbon-based fuels drives climate change. We have to get to zero emissions. But when as soon as possible? When is that for you? Pick your target. Can we wait until 2050? I don't think we should gamble with the future of civilization. Let's do it as fast as we can. So what does it mean for buildings? Well, it's simple. Net zero approach balances the CO2 emissions with an equal amount of sequestered CO2. Generating renewable energies is relatively equivalent to sequestration if you're giving RECs to others. And what does it look like for our buildings? Well, if you start off and you look at the building budget, we have a faux building budget on the left there. It shows the current use in an average building of how energy components are fed to it and fills the effective energy bucket for that building. Okay, our usage includes nuclear, renewable, and the usual carbon suspects: coal, petroleum, and natural gas. Now, in getting to net zero, the first step uses cost-effective energy efficiency measures to shrink the size of the bucket that needs filling by 1/3. With reasonable energy efficiency investment criteria, we find that shrinking the bucket by 50% should be more than achievable. Howsoever, just looking at shrinking it 1/3 leaves 2/3 that we would like to fill from the renewable energy sources that we can reach. Wind and solar are currently our most cost-effective renewable energies. On building sites in urban areas, wind is generally not an option, and finding enough space to provide this from solar is often problematic. So, this energy bucket is generally filled with a mix of solar generated on site and the purchase of renewable certificates or RECs that were generated somewhere else. That's the reality today. Looking at some terms and definitions we've got here, we've got net zero ready building and a net zero energy building. The important distinction between these two is that the net zero building has shrunk the bucket as far as is economically reasonable to reach the point where the cost of saving energy has a slightly better economic yield than the cost of generating renewable energy. Note that this point has been constantly changing as increasing in renewable generation efficiency and reductions in the cost of renewable energy continues. As this happens, the efficiency investment targets will continue to drop. So it's a dynamic thing that's being played, and it will play it back and forth. The net zero energy building happens when the shrunk bucket is completely filled with renewable energy and or renewable energy credits, certificates. So now that we've framed what net zero is, these are the steps we will try to take today to explain how we can achieve net zero cost effectively. Two major myths are at work to try to forestall net zero efforts. Forestall implies intention, I'm not sure that there is, but that's the effect. The primary ones are net zero is way too expensive and net zero is too challenging technically. Well, the National Renewable Energy Labs in Golden, Colorado debunked these myths 10 years ago when it delivered a 362,000 square foot research facility on their campus in Golden, Colorado. They delivered this with a standard design, build, construction process that brought the building in at $286 a square foot. And that included all of the solar PV needed to make it net zero. The actual building costs were competitive with costs of similar buildings in the region. Definitely not demonstration. Definitely not state of the art. Everything that was done in those buildings can be done today. No new technologies required. Okay, so another myth that we need to bust is that companies and countries need to consume more energy to grow. To bust this myth, we need to look no farther than the US context. Today, the US uses about 100 quadrillion BTUs of energy to fuel our economy. That's the bracket on the right side. We fill this bucket by producing 95% of the energy in the US and importing 5%. Of this amount, if we want to look a little closer, roughly 20% is provided by nuclear and renewable energies already. These energies are CO2 free, carbon free. Now, of that renewable bucket, I want to point out that the renewables are now equaling the amount of coal that's used in the United States. But 43% of the renewables is biomass fueled. This is still carbon-based, but is considered carbon neutral. However, this carbon neutral status only remains as long as we replace the harvested biomass with new plant growth. I need to point out that we have to have a positive approach to managing that. The myth is inherently based on the historical coincidence that energy use had tracked very well with growth in GDP. In 1973, with the OPEC oil embargo, the cost of oil more than doubled, and the US, along with the rest of spaceship Earth, was thrown into a recession. This got our attention. Eventually, the price of oil dropped back below the price before the embargo, not just to the price at the embargo. Over the next 40 plus or minus years, we have effectively halted the growth in energy usage as economic growth has barreled along. By 2016, we had only added 1/3 to our energy bucket, while we grew the economy more than twice what it was in '73. Truly, going after energy efficiency has not hurt economic growth. Myth busted. Before we congratulate ourselves too much, though, on this feat, we do have to recognize that we can still do a lot better. Why is Europe so much more efficient than the US? The primary reason is that these societies are sending proper economic signals to the public. If we really want to accelerate the pace to reversing the climate crisis, the US must send the right price signals. The incentive to accelerate change will only happen if we get people's attention at all levels. Increasing the cost of energy will get their attention. That's what happened with the oil embargo in '73. And look what that accomplished. Now let's look at the efficiency of economics. The GDP chart showed that implicitly, efficiency is judged to be cost effective, or it wouldn't have happened. So let's do a little bit more myth busting. It doesn't matter what anyone does. I can't have much impact on solving a big problem like this. You truly control directly 32% of the energy budget of the United States. It's your residence, it's your transportation. You can have an impact, a direct impact. You also put an indirect pull on all the other sectors of the economy trying to have a job and buying goods and services. With 45 years of experience, however, I can tell you that it is cost effective with no new technology to work ourselves out of this mess. Today, there's a $3 trillion market in the US to just do what's cost effective. No new technologies required. And this is predicated on assuming a 4-year payback for business and a 6-year payback for individuals. If businesses get 4-year paybacks, they get 25%. If we get 6-year paybacks as individuals, we get a 16% rate of return. These can be guaranteed. These are really readily achievable. Remember, no new technologies, very positive returns on investment. Please note that there are other reputable sources saying the same thing. McKinsey & Company in 2008 released a report documenting how the US could unlock energy efficiency in the US economy by deploying an array of NPV positive efficiency measures that would save 18 quads of primary energy use, 1.2 trillion in energy savings. This reduces our bucket for the United States 23%. The opportunities that are cost effective today in 2020 for efficiency and renewable energy are even greater. I've been doing this a long time, so I look at this more from the standpoint of the Kyoto Protocol requests that we find ways to reduce our carbon emissions to 95% of what we were putting out in 1990. If we had a target that was reducing this 25%, we would roll emissions back immediately to the level of the mid-70s. Howsoever, we have a standard where we're trying to see that people invest in 8-year paybacks for efficiency and 12 years for renewables, averaging about 10 years. If we got the 10-year savings level, we would drop our consumption back to the early 60s. Amazing reductions in carbon. This would be a return on investment of greater than 10% the first day you get there. To examine how cost effective this can be, we'll start with a residential example. Most of us are familiar with homes and their systems, so this will make immediate good sense to everybody. This is the Kimmswick home that Jordan Hyman and I built to demonstrate what we felt could really be done. It's a 3,000 square foot, all electric home designed with passive solar features. In addition to the passive features, there are other sustainability things that are key to its success. The first thing is we invested in insulated concrete forms. That's 2 inches of foam on both sides of a 6-inch reinforced steel concrete building, effective R value of about 40. We invested in state-of-the-art technology in 2007, a ground source heat pump. The ground source heat pump is trying to reject heat to the ground in the summertime, but if we install a de-superheater that intercepts that energy, we can divert and recover that energy to our domestic hot water system. Because the building was a poured concrete building and doesn't leak very much, there's not a lot of outdoor air coming in, we have a whole lot more energy efficiency, but we have to give a little bit of that back up by using a ventilation system that keeps the air fresh in the house. Doing that, the air that we exhaust, we can recoup 50% of that out and pre-temper the air coming in, both winter and summer. We did, as I suggested, passive solar features, which are no more than double glazed windows on the south wall. We installed vacancy sensors so that people had to turn the lights on when they went into a space, but they would turn themselves off automatically if they left. And then we did 100% compact fluorescence in 2007 because LEDs weren't really readily available. Today, do LEDs. You can see that our home, my home as it's stated there on our bill, would use $774 of electricity annually, a 3,000 square foot home. They told us that the average home, similar to ours, would use $1,000. We're using that in our economic analysis. Now, does it pay? The similar base frame home cost would be $337,000. The maximum extra cost you would expect for an ICF is 7%. So we're using the maximum. We asked the contractors to bid our mechanical system using both an air source heat pump and a ground source heat pump. At today's dollars, that would be an $8,000 premium to go with the ground source. The de-superheater to make the hot water would be almost $1,000 premium. So the net zero ready home, as we're calling Kinswick 1, would be $370,000 roughly. That's a $33,000 premium over the conventionally built frame home in today's market. We could, if we chose to, immediately wipe out that extra $6,000 premium in down payment through the ground source heat pump tax credits from the federal government that are still available next year of 22%. In addition, Ameren gives us an incentive of $1,800. Note, though, that you can't always depend on these kinds of benefits because they're policy driven and policy can change. Hopefully, policy will change to the better for us in the near future. So this curve on the right is the one I want you to watch. There are annual cost benefits for having done what we did, the extra dollars that we spent. The first one is a negative, though, because principal and interest payments on an annual basis are going to be $900 more than the conventional home. But our average reduction in electric costs is almost $400. The insurance we pay is about $800 less. And then there are life cycle and maintenance costs on the heat pump system that save roughly another $400. Our net benefit is $764 a year on average. I think we've demonstrated clearly, at least with that one example, a deep dive and a thorough examination of all the pieces of all the layers of the onion that you can peel back to show what the real cost benefits can be. So let's talk about the economics of renewables. Let's look at what the Energy Efficiency Administration of the DOE projected in 2015 would be the levelized cost of new generation built in the 2020 timeframe. Now, they used levelized cost of energy and they compared it to coal. Now, renewable energies are listed there in green. 3 years later, after they published this in 2015, Deloitte came out with a global renewable energy trends analysis. And it said that wind would range in 2018 between $30 and $60 a megawatt hour. They also suggest that solar is going to be $43 to $53 a megawatt hour, and that conventional fuels would be producing electricity between 42 and 78. I'm sorry, I mean, these are not projections. These are realities. These were the values that Deloitte identified. This is where the DOE recommendation or projections of 2015 said things would be. This slide is not to show how far off the mark the EIA was just 3 years later, but to underscore the fact that the market moved faster than was expected to deliver lower renewable energy costs. I think that's a trend that we can continue to count on. Now, solar here will be considered to meet the load needs at various levels of energy consumption in this home. We're using a whole lot more electricity in the wintertime, but most of the energy is relatively flat throughout the year. We're not seeing the same increases that people normally see with air conditioning in the summer. It's because being ground coupled, we moderate or flatten out that curve. The only reason we have spikes in the winter is because the nature of the heat pump is it can't produce 100% of the energy needed for heating on very, very cold days. So we're buying direct electric resistance. If we put solar in and we just want to not overproduce, we want to make sure that all of the electricity is mostly used on site, then we would only put in 6.5 kW to meet the needs of the house. One other reason we do this is because if we produce more than that, the net metering rules for Ameren, Missouri are, if you produce more than you use in any 1 month, Ameren buys it back, but they only give you 1/4 the value of that energy. They buy it back at wholesale rate, 2.5 cents a kilowatt hour. Howsoever, from a net zero standpoint, we might want to put in an additional 2.5 kW array so that we fully eliminate our electric utility bill. It means that we don't fulfill all of it with solar in the winter, but we've overproduced in the summer, and we move that green swatch above the red dots over to fill in under the red dots. This means that we're now considered net zero without investing in other sequestration options or buying RECs. So what's the economic value of doing this? You can see that the cost is linear, and we've rated it at $3 a watt installed. That's comparable to average prices in the St. Louis, Missouri area. There are incentives that Ameren will pay you that are still linear, so you don't lose that. And the tax benefits that you get from the federal government are linear. If all of it is sold at retail value, or you're offsetting retail value from your Ameren costs, your payback is 9.8 years in Missouri today. Now, if you are upping yourself to the 9 kW and you are considering yourself totally net zero, you still have a handsome payback. It's 11.6 years, which is still less than the 12-year limit that we're asking you to consider investing into for renewable energies. That's an 8.6% yield. So I believe that answers the question of the economics of renewables. I consider them to be within economic reason today in the St. Louis market. So let's define and look at the RECs and other offsets and things like that we were talking about. Renewable energy certificates are the green component of the value that they can, in effect, separate from the actual electrons generated from the renewable energy process. It has market value because policies that have been established require utilities to make sure that they are generating renewable energy as part of their power generation portfolio. With this market now firmly established, there are many opportunities to sell these RECs to people seeking to be net zero, but for some reason can't. Okay, this slide demonstrates why entities that want to be part of the climate solutions might need to buy RECs to demonstrate their net zero commitment. Buying RECs will allow them to participate with the larger community. This purchase will support others located in areas where they can economically produce an abundance of renewable energy. It's a team effort. The crew members are working together. As mentioned before, our homeowners association has policies that kept us from being able to put solar on, and the net metering issues that I've listed here also can affect the decision to go for renewable energy on site. But since our homeowners association would not allow us to put solar on back then, we chose to purchase what are called RECs. And they were being sold by Ameren through what was their Pure Power program then, and it cost us $0.015 per kilowatt hour. In other words, we added almost 20% to the cost of our electricity in order to claim that we're renewable or net zero. In the 2020 market, Ameren will sell you the same Pure Power RECs for $0.01 a kilowatt hour. It's showing the anti-inflationary nature of how much renewable energy we're producing that the RECs can't command a market value. The price has gone down. Now, another local example that I think is important to illustrate this is Anheuser-Busch InBev owns or buys RECs now to replace 100% of its brewing energy used in the US. The two examples are they're in partnership with an Oklahoma wind farm that can wheel the power to their plant in Houston, Texas. Now, this has to do, again, with policy decisions. Texas and Oklahoma are deregulated utility markets. Missouri is not. So in Missouri, they can't wheel the actual electrons to us, but they can give us RECs, and they buy those RECs from a solar farm in Pecos County, Texas. Now let's take some design steps to net zero. This slide is a little bit dense, and this is set up for new construction. The first thing I think that is most important is establish a smart energy investment policy. And you do all the normal things you do in planning and masterminding a policy. We're just adding the energy components to it. You establish your energy project requirements, but you're also going to review the site if we're going to be required to install renewable energy options. So there's a site energy analysis that goes in that's deeper than what you normally do on a site. I would also recommend that any building done implement the advanced commissioning process during the design cycle according to LEED. This gets another pair of informed eyes working with the architect and the engineer to make sure that all energy opportunities are taken maximum advantage of. That becomes the building baseline for the model that you're going to compare yourself to in order to strive to use design to achieve net zero. The energy efficiency target that you should set should be at least 30% less than that allowed by the code. You're going to compare the baseline building's energy use and energy costs to the actual design for compliance with the energy policy. Then you're also going to design and evaluate renewable energy for also compliance to see if you can actually fill your entire bucket by making the building more efficient and then using renewable energies on site. If you can't, you'll have to go into a REX mode. And there are opportunities to do it multiple times, but then you're going to eventually execute. But after you execute, you need to measure, verify, and educate. For renovation, you document your current energy and water use and any renewable energy production that you have on site. Then you perform an ASHRAE Level 2 energy audit, developing measures for efficiency and renewable energy as you go along. Now, let's talk about this energy policy. Again, it's about mindset. We can invest so that we no longer waste our money on bad energy practices. Reaching these reasonable rates of return on investment will make sure, however, that we truly are saving the planet. This is what we would suggest be a sample, smart energy investment policy. It has to be specific, measurable, achievable, realistic, and time-bound. Now, this is addressing from the design's point that you need to orient the building properly on the site. Make sure that passive design principles are not ignored. Then you also will evaluate the site for what renewable energy production opportunities exist to finish filling your energy bucket. There needs to be a holistic, integrative design approach driven by sound economics. What has happened in the past isn't working. We need to disrupt the current processes. For instance, if we're talking about economics, we've got first costs, energy costs, maintenance costs, and life cycle costs. These shouldn't be in their separate silos. We have to refashion our ways of thinking about paying for things, destroy the silos and their compartmentalization, and make it an integrated process that understands the interrelatedness of costs over time. Make decisions today while being mindful of our impact on the seventh generation to come after us. We've already shown that it's cost effective. Why aren't we doing it? Okay, there's a few other myths we need to bust on the engineering side. If some is good, more is better. You've got to be sure that you know when to stop and you use the guidelines that we've given you for efficiency at 8 years to make sure you don't put an extra inch of insulation in when it's not paying for itself. Each inch of insulation will save less energy than the inch you put in before. Bigger is not better, bigger is only bigger. And typically that means it's oversized and it's going to be less efficient. Less is better. If I have one piece of equipment at 100%, a lot of the hours of the years, it's a lot less efficient than it could be. If I buy 3 modular pieces of equipment that give me the same output, I now can follow the loads a lot more efficiently. Yes, it may cost more to maintain 3 pieces of equipment than it does 1, but your energy savings will more than offset that maintenance cost. In addition, more pieces of equipment give you higher resiliency in case one goes down. Only design matters. Operations don't count. No. The design gives you the opportunity to be efficient. It's operations that maintains your staying efficient. You got to do it and create staff incentives and rewards for maintaining performance. Invest in your people. Give them a reason to make sure it stays where it needs to be. They're your eyes and your ears. Let them do their job, but make sure that it's rewarded when they do it effectively. Now let's look at some quick case studies. This shows what has happened at the Danforth Center. They expected to be very energy efficient. However, design problems thwarted that attempt. We were asked to assist them and tackled 2 major issues. They were using too much outside air and the boilers were way oversized. Again, bigger is not better. Okay? We dropped the outdoor air intake from 15 to 8 air changes an hour, almost cut it in half. We tore out 3 10 million BTU boilers that were so oversized they could not stay and operate in the summer during the reheat loads. These were replaced by 4 2 million BTU boilers, and they were condensing. The green line shows the cumulative savings, and the red line shows the cost of making the investments in energy efficiency. The first start paid it back in 21 months, and after that, we had more than enough money to pay for the other improvements. They spent a total of $600,000 and saved $2 million. This netted a 34% ROI over 10 years. They cut their carbon emissions 20%. Now let's look a little bit at how we can scale it. This was a neighborhood that we did an analysis of for a community energy system back in 1981. It was 168 dwelling units, and our remodel efforts suggested that we could reduce the heating costs in the site 50%, as well as the cooling costs, just with thermal transmission improvements. And passive solar in the winter would drop the heating costs another 20%. If we redirected the neighborhood's costs for disposing of waste, sewage, biomass, trash, and garbage, we could generate the energy needed. Again, taking waste and going to energy, combined heat and power again. We can burn this. We can reduce landfill waste. There are multiple of these in the United States that are burning municipal solid waste. In Sweden, the law says you cannot landfill any organic waste. You do have to burn it. So these become, small DERs spotted around the countryside supporting each other. And in addition to just burning it, we can make renewable natural gas if we use anaerobic digesters or some other incipient technologies. And there are other additional benefits in terms of nutrient recovery that you can make for the ag sector and co-products that can be used also in the ag sector. A small town in Texas used PPAs, power purchase agreements, to install 144 megawatts of wind in North Texas, 150 megawatts of solar near El Paso. Through the PPAs, they had delivered to their gate more power than they needed at 4.5 cents a kilowatt hour. And it was now significantly less than the former power they contracted for from the grid. At the end of the PPAs, the city can own the assets. Unintended consequences for the environment are, it saved lots of water. It takes a lot of water to make a kilowatt hour. These are not made using conventional processes that require cooling. Next steps are to figure out how to store this energy so it's always available. So a couple remaining obstacles and things to talk about. Some of them are real, some of them are imagined. Cost effectiveness, I think we've already dealt with that. We know that it's cost effective. As for financing, there's a large array of means and measures to pay for both efficiency and renewables. A PPA, for instance, tackles renewables as a market, and the Energy Services Agreement, the ESAs, tackle efficiency. It's clear that there are no credible barriers in financing going forward. The technical solutions, not an issue. History has shown that technology will get even more cost effective. The real issue is perceptions and motivation. We're in an age of misinformation. There are powerful political and economic agendas behind climate denial. Competition for the attention of decision makers above the din of that noise is their real issue. Old habits die hard. We've never done it this way. Silo thinking, we've already talked about that. When you have an integrated energy and economic expertise on your team, you've got the champions that will make it happen in your organization. Foster that. Establish, again, a smart energy investment policy. Link management incentives to achieving the energy goals and make those same incentives go down to the ranks. Corporate education and training is required to make this sustainable, and you do have to invest in the energy skill sets of your staff. There are many benefits beyond financial. There's marketing benefits. You diversify your energy supply, you've improved your resiliency, you're also mitigating the climate risks, and you're improving the overall community environmental quality. We hope you've benefited from this presentation. We believe that we've shown that the value of establishing energy master planning, guided by smart energy investment policies, will generate significant benefits. Digging deep into the economics, make sure that you can show other people that it is cost effective for you to reach your net zero goals. There are investments that will add value to your property, and money that you save will grow over time as fuel costs increase. Approaching the problem holistic, busting silos is a great way to make sure that your methodology will succeed. That the cash flow in your current energy and waste bills, along with financing options available to you, can make sure that you implement your net zero solutions and immediately find yourself in a cash flow positive mode. I thank you for your attention. Just want to remind you, it's in our hands and it is up to us.